Hello everyone, my name is Robert Griffin. I'm a research scientist with IHMC, and I'm here today to talk to you about some of the skills that are needed to actually make humanoid robots useful in the real world, and also kind of what IHMC is doing to help develop some of these skills. So before we get started on what some of the requirements actually are, it's important to identify what some of the potential application for robots like humanoids are. Because of the inherent capabilities of robots that are shaped like people, there's an incredibly broad number of applications. But really, there's only a few that you can think of that could potentially be both cost-effective and feasible where a humanoid is necessary. And these typically have the attributes where a large amount of flexibility is required in the capabilities of the platform in order to properly perform the task. And some of these kind of tasks are things like emergency response, where you have to have a robot actually go in and investigate an area that's dangerous for a person to be. Or another possible application is exploration of unknown environments, such as a lunar surface or even hopefully one day Mars. And then another possible application would be bomb technicians. So kind of these types of really applicable tasks are things that require a lot of flexibility, like I said, but also where you would really want to send a human if it wasn't so dangerous. So the thing that we're kind of focusing on is the development of robots that can take the place of a human and be actually an avatar for them in those environments. And fortunately, a lot of these tasks don't require really high speed. If I think of a bomb technician, I don't think of someone rushing through something very quickly. I think of them being methodical. They also require a large amount of flexibility and dexterity in what the system is actually capable of. And then they also require reliability. So one of the first sets of skills that we talked about was being at least an operational level of speed. And so when we look back at our performance from the DARPA Robotics Challenge, you can actually see that 65% of the time that we were there, the robot was just standing there. It wasn't moving, it wasn't doing any tasks. It was just the operator trying to tell the robot what it should do and examine the sensor data. That means that we don't even have to increase the physical capabilities of the robot at all. It doesn't have to be faster, it doesn't have to move more quickly, anything like that. If we can just cut down on this idle time, we just made our robot 3 times as fast. And this is really important. If you think about the way that we were interfacing with the robot at the time, we were actually placing individual steps in the world. This is different than if you fast forward to today, the way that our approach is. Here you can actually see this is work that we wrote up for the Humanoids Conference from this last year, where the robot is actually determining where to step on its own. So instead of having the operator go and individually place footsteps in the world, which is difficult for them, if you can't see the environment, you're having to utilize the robot's perception sensors, figure out a good way of representing the environment for you to plan over, and then individually place where you think those steps should be in the world, as opposed to allowing the robot to develop some model of the environment and then plan its steps autonomously. So in this approach, we're actually using an A-star algorithm where we are mapping the environment using planar regions, which I'll show you in just a second, and then snapping the polygons of the feet to those planar regions, which enables us pretty robust locomotion over relatively complicated environments like this cinder blocks field. One of the things you will notice, though, throughout this video, there are little pauses before the robot starts to move. And actually, we cut out some of those frames because they're not fun to look at because the robot's not moving. But in that time, it's actually having to collect sensor data. So I mentioned, we're planning from the beginning all the way to the end. And so in the meantime, we're having to develop or map out what the environment actually looks like. So here we developed this planar region segmentation algorithm using the LiDAR on the robot's head. And that has, it's pretty accurate given the fact that it's LiDAR, but it does have some inherent drawbacks of it's kind of slow. So we have a single spinning point LiDAR and the Hakuyo on the head, so you don't have a very dense image of the environment, and then you're planning over this long distance, meaning it takes the robot about 10 to 20 seconds to actually map out this environment accurately enough for it to develop plans. And that's not really realistic. That's introducing a pretty long pause. So what we really want to do is cut that time of perception down dramatically. So to do that, we can actually look at kind of a way that humans do it. So this is a study that was done by John Mathis, and I love showing these videos because they're some of the coolest videos I've seen on this kind of stuff, where you look at where the human is actually stepping. He's looking pretty focused. You can see on the bottom left here, he's pretty well focused on 1 to 2 steps ahead. You're not looking at the full horizon of where they're trying to go. And this is in much more complicated terrain than what we had the robot operating in. So clearly, people are not looking and planning and modeling over this entire time horizon like what we're doing with Atlas previously. So we've been moving in this direction. So we've introduced a Intel RealSense onto the pelvis of the robot, and that allows us to actually get these local, accurate images of the environment. We can then, use the point cloud to actually do the environmental segmentation that we were doing with our LiDAR previously and develop these models of the environment. So we actually are having to here also do some localization in order to stitch the images together properly. Well, so you can see here, once we have these local planar regions that we're able to get at a high rate, the robot is actually able to extract the planar regions from them and then plan over those in real time. So we converted our A-star planner to actually an anytime A-star planner, and we're just constantly streaming those results to the robot. Here we have an operator indicate a goal location to the robot, which it just reached, and then the robot is just constantly trying to take the best steps to get to that goal. And here in and then we have it actually pause to allow it to build up a representation of the environment from the LiDAR, to then have the operator place another goal where the robot will then plan automatically to and develop and then use the data from the RealSense in order to actually plan the footsteps. Making robots that are useful only has a small element of locomotion in it. Yes, the robot needs to get from one point to another, but then it needs to be able to actually do things when it gets there. And for certain manipulation tasks that it can be relatively well defined, but for others, it's very complicated to define a good set of objectives that allows the robot to autonomously perform. I'm not a manipulation researcher, and even I know how incredibly complicated that task is. So to kind of start exploring this space to allow a more flexible approach, we've actually been looking at using virtual reality for directing the robot. So here you can see our operator in the corner is wearing an HTC Vive in this interface, and it is streaming inputs directly to the robot, where we're actually having it go through this inverse kinematics optimization to make sure that they're kinematically feasible and also maintain balance and avoid collisions, but then that's going directly to the robot. And we found that this is actually extremely powerful interface because it allows you to direct the robot in an intuitive fashion that allows you to do tasks that you've never seen before. And we started using that pretty extensively. So here we have the robot or the operator, telling the robot where to step, and it gets to a certain location, and then it can't go any further. There's debris blocking the way. So we have the operator then get into the virtual reality interface, and he's able to relatively quickly clear the environment. So this is in, looks like slightly sped up time, probably about 2 times speed, partly because the robot's just not super fast. So I don't want to bore you all as you watch it move. But he's able to clear these 2x4s out of the way, and then actually it's kind of funny. He decides to get a little creative and tosses some of them and then knocks over the cinder blocks and allows the robot to be able to keep moving. So using this virtual reality interface, he's able to really robustly open the barrel in a variety of different ways. So here we had him do this fun, like use this pole to do it. Unfortunately, the left hand is actually broken, so we can't do anything with that, which is what, other than subtly kind of move the barrel around. And he's able to do a lot of different approaches using this virtual reality interface. Using these virtual reality interfaces in autonomous footstep planners has now started to allow us to build up a library of automated behaviors. So one example behavior is actually having the robot be able to go up and down stairs. So in this task, the robot is told, walk to the bottom of the stairs, and then we have the robot turn around and walk to the top of the stairs. Using this kind of behavior architecture, we're actually able to have the footstep planner be tuned so that it works on stairs, and we send those parameters over when it's time to go up and down the stairs. And we've been able to get this to be pretty reliable. One of the challenges is if we're using the LiDAR trying to map out the stairs from the beginning at the bottom, you have a pretty bad angle of perception. So kind of one of the next big steps here is going to be to tie in this real-time, real sense-based walking in planar region extraction. The task has been, the ability to go through doors. Doors are one of the big challenges facing robotics when you think about their ability to navigate the world. If there's a door in the way and they can't open it, then they can't go there. It doesn't matter how well they can walk and navigate through the building. If you can't open the door, you're blocked. So in this case, we developed a door opening behavior where the robot first recognizes whether it's a push or pull door. We're doing that with just basic QR codes. We're hoping to eventually replace this with some kind of machine learning based object recognition. Then the robot finds the door handle and has a kind of scripted motion in order to actually open the door, but we do have some of these feedback elements tied in where it does pull and look for door motion. We don't have a good way yet to recognize whether or not the robot's gotten a good grasp on the door handle. I think that's a very interesting part of the problem, but with the ability or with the quality of the arms on Atlas, it's just not really possible to do that kind of thing. Then the robot autonomously finds a path to get through the door, makes it to the next one, and you can see here that the next door is a push door, and so this is actually much easier. We've been able to do push doors autonomously for quite a while, and it will actually go and recognize that it's a push door from the QR code, open it, and go through. One of the interesting challenges of this is to build in this kind of idea of resilience where the robot can detect failures. So did my hand slip off the door by it not unlatching, or is the door not moving? And then have it actually be able to re-execute its plan in order to open the door again in a reliable fashion. So as I'm sure many of us remember from the DRC, we know humanoid robots still are also not super reliable. They fall, in this case a lot. They have gotten definitely better. Some of the great stuff coming out of other groups has really been able to highlight some of the reliability of the locomotion. But the question is, people also fall on not an irregular basis. And the big question is, what do we do when that happens? So the robot has to be able to survive these kind of falls, both physically, but then also to be able to recover from these type of falls and continue performing its tasks. So to do that, we've actually started to build a new robot called Nadia. The goals of this robot are having a high range of motion, high speed and power, relatively compact profile, and most importantly, the ability to make contact with the world with pretty much any link of the robot. And we made a lot of progress, so here's the kind of our latest model of the robot. And I'm going to go in and talk a little bit more about it. So Nadia is powered primarily by these linear hydraulic actuators from Moog, the ISAs. We also developed some custom electric liquid-cooled actuators for the hip yaw and spine yaw joints. So we have two hydraulic ISAs at each hip joint that work in parallel for the pitch and the roll. And then we're actually able to the goal here was to be able to get at least 100 Newton meters of torque and 12 radians a second at any position throughout the hip range of motion. And we were able to do some clever mechanism optimization that enabled this to be possible using the configurations that you see here, where we have this dual 4-bar mechanism. We're also able to get about 140 Newton meters out of each of these electric actuators and around 9 radians a second. For the knee, we designed it using this cross-linkage kind of approach because one of the big challenges is if we want to be able to have a high range of motion, we actually have to do the hydraulic hose routing through the knee joint in order for it to be protected. So by designing it in this way where you have kind of a 4-bar linkage built into the knee, you're able to have a constant path, a length for the hydraulic lines to go through the knee. And we're able to do this and get around 160 degrees of range of motion to allow the robot to do these kind of really deep squats. And the nice thing is we also designed it so that we can have really high torque at 250 Newton meters through the less bent configuration of the knee, so between that 0 and 90 degree, but still have a relatively high force output when it's higher bent at around 100 or at its 160 degree full range of motion. Using our dual 4-bar design at the hips, we're actually able to get a really high range of motion, which in the pitch we're able to get about 142 degrees, but most notably is actually in the roll, where we're able to roll really far out to 56 degrees and then also get a really high internal rotation of 28. And this high range of motion allows for really great crossover steps as well, which is something that we've wanted to do to be able to really maximize the robot's mobility. So it's actually able to touch its toe to its heel while walking with almost completely straight legs, and it can actually go way past the leading foot if you allow that front leg to bend, as you see here. On the ankle, we just used a traditional approach where we have the parallel actuation, and we're able to get 105 degrees in pitch and then about 50 degrees in roll while having still a very high pitch output. So unfortunately, these are the only size ISAs that they make now. They were going to have a smaller size and we were going to use it here. It was going to be great, but just because of market availability, the large ones were the only ones that are available. So we're able to get incredibly high torques out of the ankles. In order to have the robot protect itself in the case of falls or interacting with an environment, we're utilizing carbon fiber shells, both for protection but also the actual load-bearing structure. This is working out really well. The carbon fibers has demonstrated that it's both lightweight and strong, with about the same strength as aluminum 6061, but also making multiple versions is relatively inexpensive. Once you've tooled the molds, you're able to actually fab up additional components pretty cheaply at about $120 per shot. We've then utilized some of the early designs in a bunch of different tests, both testing the deflection where we lock the joint out, repeated pressing of high loads, in this case about 100 pounds, as well as some jumps where we actually broke the rod end on the actuator, which was not where we were expecting to see it fail. We've also been exploring a lot of testing of the force control. As a lot of you probably know, our approaches for controls rely pretty heavily on the ability to do accurate force control with the robot. So this is pretty important, and we actually noticed, one of the things that we actually noticed was when going really quickly on step inputs, we would get a lot of problems with the overshoot on the force control, mainly because the valve speed can only move so quickly. So to address this, we actually did some exploration into pilot-induced oscillation, which kind of had a similar problem. And after introducing this basically lead lag filter, you can see here we were able to really get that to not overshoot much at all. It's a little bit slower in response now, but we're able to get really good force control out of it and avoid this kind of ringing that we were seeing where it would overshoot and then vibrate. One of the last things we're kind of exploring with this robot is for state estimation. So we've introduced IMUs into each of the links, and we're able to use these IMUs to help estimate the velocity of the joints as well as the poses. And we've actually been getting really good results. We're trying to design the robot in such a way that it doesn't use absolute encoders of the joints and instead just uses the shaft length measurements inside the actuators to back out the joint positions. The problem is this makes it pretty susceptible to things like backlash. By adding these IMUs in, we're able to compensate for a lot of the backlash in our velocity estimates, which we think will be really beneficial when it comes to actually testing out the balance. With that, I'd like to thank a lot of our sponsors and partners that have worked with us, especially like IIT working very closely with the design or the development of some of our force control techniques, and Haloti with supplying us with awesome electric motors, as well as just many of our other vendors and partners, and our funding agents, ONR, NASA, and DTRA. And lastly, we couldn't do it without having a great team. So, this is a little bit old. We haven't been able to get together as a team and get a new picture in a little while, as you probably could all guess. But, this kind of work is only possible by having a great set of people that are willing to work incredibly hard to make it come to life. And with that, I'd like to open the floor for any questions, and thank you all for listening.